In Chapter 17, we introduced the wave phenomenon of diffraction, which described how sound waves could bend around obstacles or around the edges of openings. Light waves also exhibit diffraction effects. Let's first begin by considering how sound waves diffract through an open doorway, as shown in the figure. To do this, we will incorporate Huygens' principle, which describes how a wavefront that exists at one instant gives rise to the wavefront that exists later on. This principle is stated as follows. Every point on a wavefront acts as a source of tiny wavelets that move forward with the same speed as the wave. The wavefront at a later instant is the surface that is tangent to the wavelets. The figure shows the top view of a plane wavefront of sound approaching a doorway and identifies 5 points on the wavefront, just as it is leaving the opening. According to Huygens' principle, each of these points acts as a source of wavelets, which are shown as red circular arcs at some moment after they are emitted. The tangent to the wavelets from points 2, 3, and 4 indicates that in front of the doorway the wavefront is flat and moving straight ahead. At the edges, however, points 1 and 5 are the last points that produce wavelets. Huygens' principle suggests that in conforming to the curved shape of the wavelets near the edges, the new wavefront moves into regions that it would not reach otherwise. The sound wave then bends or diffracts around the edges of the doorway. This is why a person who is not standing directly in front of the doorway can still hear the sound. Since light is also a wave and undergoes diffraction, you might ask how come we can't see around the door. In fact, light does bend around the door, but just not that much. We will see that the extent at which the wave bends around the edges of an opening is determined by the ratio of lambda over w, where lambda is the wavelength of the wave and w is the width of the opening. The photographs illustrate the effect of this ratio on the diffraction of water waves. The degree to which the waves are diffracted or bent is indicated by the 2 red arrows in each photograph. In part A, the ratio lambda over w is smaller because the wavelength, as indicated by the distance between the wavefronts, is small relative to the width of the opening. The wavefronts move through the opening with little bending or diffraction into the regions around the edges. In part B, the wavelength is larger and the width of the opening is smaller. As a result, the ratio lambda over w is larger and the wavefronts bend more into the regions around the edges of the opening. We expect that light waves will do the same thing if the ratio lambda over w is made large enough. This will occur when the width of the opening is comparable to the wavelength of the light. The following figure shows parallel rays of light falling on a narrow slit and illuminating a viewing screen that is located far from the slit. Part A of the drawing shows what would happen if the light were not diffracted. It would pass through the slit without bending around the edges and would produce a single line image of the slit on the screen. Part B shows what actually happens. The light diffracts around the edges of the slit and brightens regions on the screen that are not directly opposite the slit. The diffraction pattern on the screen consists of a bright central band accompanied by a series of narrower, faint fringes that are parallel to the slit itself. In other words, we see an interference pattern. To help explain how the pattern of diffraction fringes arises, the figure shows a top view of the plane wavefront approaching the slit and identifies 5 sources as Huygens wavelets. Consider how the light from these 5 sources reaches the midpoint on the screen. To simplify things, the screen is assumed to be far from the slit so that the waves from each Huygens source are nearly parallel. Then all the wavelets travel virtually the same distance to the midpoint. Their optical path length difference is 0, and they arrive there in phase. As a result, constructive interference creates a bright central fringe on the screen directly opposite the slit. The wavelets emitted by the Huygens sources in the slit can also interfere destructively on the screen, as the figure illustrates. As we move up along the screen away from the central bright fringe, we come to an angle theta that locates the first dark fringe. Here, the wavelet from source 1 travels the shortest distance to the screen, while the wavelet from source 5 travels the farthest. Destructive interference creates the first dark fringe when the extra distance traveled by the wavelet from source 5 is exactly 1/2 wavelength, as the colored right triangle in the drawing indicates. Under this condition, the extra distance traveled by the wavelet from source 3 at the center of the slit is exactly 1/2 of a wavelength. Therefore, wavelets from sources 1 and 3 are exactly out of phase and interfere destructively when they reach the screen. Similarly, a wavelet that originates slightly below source 1 cancels a wavelet that originates that same distance below source 3. Thus, each wavelet from the upper half of the slit cancels a corresponding wavelet from the lower half, and no light reaches the screen. From the figure, we see that the first dark fringe is given by sine theta equals lambda over w, where w is the width of the slit. Similar arguments hold for the higher order dark fringes, and the general result is the following. Sine theta is equal to m lambda over w, where m is equal to 1, 2, 3, etc. Between each pair of dark fringes there is a bright fringe due to constructive interference. The brightness of the fringes is related to the light intensity, just as loudness is related to sound intensity. The intensity of the light at any location on the screen is the amount of light energy per second per unit area that strikes the screen at that point. The figure shows a graph of the light intensity along with the single slit diffraction pattern. The central bright fringe, which is approximately twice as wide as the other bright fringes, has by far the greatest intensity.